The following is a review of for Python and Excel, where we'll solve two different kinds of problems. The first is integrating a function, and the second is solving a system of equations. So for problem 1, we want to find the integral of cosine x over x dx with bounds from 1 to 2. This will be a numerical integral so that we can integrate the function and find the value. The library that we want to use is SciPy's integrate library, and this specific function is quad. So we'll go import, we'll go from SciPy.integrate, import quad, and import numpy as np. Now, the first thing to do is define the function that we want to integrate, cosine x over x. So we go def f of x, and we can simply return np.cosine of x divided by x, and that's it. Then to integrate the function, we can go I equals quad, and quad takes the function that we are integrating and the bounds, 1.0 to 2.0, and we can print I. And that's it. Here's the integral, and this is an indication of the error. So really, we could go I is quad 0 in order to just get the first element of the list that's returned. So that's all there is to doing a simple integration. The second problem is to find one of the solutions to the following system of two equations and two unknowns in y and z. When we formulate these kinds of problems, we want to formulate them as f of x equals 0, where f is a vector function, so this would be f0 and this would be f1, and our unknowns would be a vector x, where x0 is y and x1 is z. Right now we have y on the left-hand side and this quantity on the right-hand side, so we should take this quantity and subtract y from it so that we have a function that equals 0, because this is the form that the solvers like to use. So the first thing to do is to define the function def f of x, where x is an array that we pass in, and we'll return an array for the function. If we want to make it easier to write our equations, we can do y equals x0 and z equals x1, and then we can write f0 equals z cubed minus 3.0 times z squared plus 5.0 times z plus 3.0, and f1 is z plus 10.0 minus y, and then we need to make an array out of that, so we can go and return np.array f0 and f1. So there's our function. Then we need an initial guess for the function, so we can go x0 equals np.array, and we choose some initial guess, 1.0, 1.0 say, and then we call the function. X equals fsolve, give it the function and the initial guess. Now, in order to use fsolve, we need a library, so we go from scipy.optimize, import fsolve, and it solved the problem, and then we can print out the result, print x. And in this case, this is our unknown y, and that's our unknown z. If we want to get a more pretty output, we could type y equals and z equals, and then percent x0 and x1. And that would show our answer a little bit more intelligently. Okay, the third problem is to simply repeat this problem that we just worked using Excel. So let's go ahead and do that. we write our two unknowns. Let's blow this up a little bit. So we have y and z, and we give initial guesses for those, 1.0 and 1.0. Then we can write our functions, f0 and f1. So f0 is equal to, and maybe we'll name these yvar and zvar. So f0 will be equal to zvar cubed minus 3 times zvar squared plus 5 times zvar plus 3 minus yvar. And f1 equals zvar plus 10 minus yvar. And we'll adjust these using the solver so that these are 0 like they should be. So we come up to the solver, tools, solver, and we want to make this function a value of 0 by changing our unknowns. And we'll do subject to the constraint that our other function is also 0. And let's not constrain the variables to be non-negative. And then we can hit solve. And it's working on it. And it found a solution. Let's see, is it the same as we had before? Nope, 9.54 and minus 0.45. It's not the same solution, but it does zero the function, so it is a solution. If we give it a closer guess, let's try that. 9.5 and minus 0.45. 9.5 and minus 0.45. And then try the solver and see if it will find that solution. And solve. Nope, didn't get to it even with that. So let's check our function, see if we did it right. Zvar cubed minus 3 zvar squared plus 5z plus 3 minus yvar. And zvar plus 10 minus yvar. Let's see if we coded this one correctly. Z cubed minus 3z squared plus 5z plus 3 and z plus 10 minus y. So that looks okay. Let's, if we put the actual value and see what it gives us, 9.54384 and minus 0.456164, and it looks like we probably entered our function incorrectly. Yeah, sure enough, we didn't subtract off y when we did this one, so the equations weren't the same. So if we resolve those, we have 12.516, 12.516, and 2.51598, and now they're basically 0. So an easy way to check, just by coding it up again, it's very easy, as we can see, to make a calculational error in entering the formulas. There's another way to solve these equations. We can regard whatever the value f happens to be, 1 and 1, as an error, because it's supposed to be 0. And we can find the square error for these quantities, square error 1 and square error 2. So this, well, so this would be equals that function squared, and this one is the other function squared, and then we can compute the sum of the square error, just adding those up, equals the one plus the other, and then we can we can adjust our unknowns to minimize the error, and that will combine both of these. So let's try that. Tools, solver, and then we can set this to be minimum by varying our same cells. In this case, we don't need an extra constraint because minimizing the square error will attempt to zero both of these at the same time. We can hit solve. And it found the solution. Great. So we can see in this case the sum of the square error is practically zero, and it found the solution here. So there's two approaches for solving a system of two equations and two unknowns using Python and Excel.